We've sent probes to the very edge of our solar system and peered back to the dawn of time itself. Yet, there's a frontier we know shockingly little about. And it's right here, beneath our own feet. For a long time, it was a stunning fact that we had more detailed maps of the moon's surface than of our own planet's seafloor. While recent efforts are rapidly closing that gap, the world hidden beneath the seabed remains a geological history book with its most important chapters still waiting to be read. There's a mission that sounds like pure science fiction: to drill through miles of solid rock at the bottom of the ocean and, for the first time, touch the Earth's mantle. This isn't just about digging a really deep hole. It's a journey into a realm of crushing pressure, absolute darkness, and unimaginable heat. To even try, engineers have had to invent technology that pushes the very limits of what's possible. This is the story of that mind-bending engineering, a quest to conquer the inner space of our own planet. The unmovable ship. The first impossible problem starts before you even think about drilling. Picture this: you're on a massive vessel in the middle of the Pacific. The nearest land is 1,000 miles away. Below you, the seafloor is over 2 miles down, far too deep for any anchor. Your job is to keep this colossal ship perfectly still, not for an hour, but for weeks or months, while winds, waves, and currents batter it relentlessly. How do you do it? The answer is one of the unsung marvels of modern engineering: a dynamic positioning system, or DP. A DP system is the ship's brain and muscle, working in perfect harmony. The brain is a computer that uses an array of sensors: satellite GPS, sonar beacons on the seafloor, and wind sensors on deck, to know the ship's exact location, often holding it with remarkable precision. This brain is connected to a series of powerful, multi-directional thrusters around the hull. These aren't just for steering, they are constantly firing. A gust of wind hits from the port side? The starboard thrusters instantly fire to counteract it. A strong current pushes from the north? Other thrusters work to hold their ground. The ship never truly stops moving. It's in a state of continuous, controlled adjustment, making thousands of tiny corrections to hover over a single point miles below. This technology is a foundational piece of the puzzle, without which this kind of deep ocean drilling simply couldn't happen. Conquering the abyss with the ship held in place, the next challenge is the descent. The trip to the seafloor is a journey into an alien world. As equipment goes down, light fades to absolute black, and the temperature plummets to near freezing. But the biggest enemy is pressure. At these depths, the weight of the water exerts a force that would far exceed the design limits of a military submarine. In this hostile environment, humans can't intervene directly. So, engineers send down their robotic eyes and hands, remotely operated vehicles, or ROVs. These are sophisticated underwater robots, tethered to the ship by a cable that supplies power and carries data. Guided by pilots in a control room, these ROVs use powerful lights to cut through the darkness, high-definition cameras to act as the team's eyes, and incredibly precise manipulator arms. They are the deep-sea mechanics, guiding massive pieces of equipment into place, locking connectors, and turning valves on the wellhead, all in a place no human could ever survive. They are an essential link connecting the engineers on deck to the pitch-black, high-pressure world of the abyss. This extraordinary level of engineering is what allows us to attempt what was once considered impossible. It's a true testament to human ingenuity. If you're fascinated by the technology that pushes the boundaries of exploration, make sure to subscribe and join us for more stories from the world of extreme engineering. The unbreakable rock. Once the connection to the seabed is made, the main event begins: drilling through miles of the Earth's crust. This isn't soft dirt. It's layer after layer of dense, abrasive rock like basalt. The friction alone generates incredible heat, and the Earth's own geothermal gradient means the temperature can rise to hundreds of degrees Celsius, hot enough to weaken or destroy standard equipment. The drill bits used for this are masterpieces of material science, forged from super-hardened steel and studded with industrial-grade diamonds or tungsten carbide cutters designed to grind away at the hardest rock. But the bit is only part of the solution. A key piece of technology is a highly engineered fluid often called drilling mud. In many industrial operations, this mud is pumped down the drill pipe and circulates back up, performing several critical jobs at once. It cools the drill bit, carries crushed rock cuttings back to the surface, and its weight prevents the hole from collapsing. For scientific drilling, where protecting the pristine deep-sea environment is paramount, this process is often adapted. Techniques like riserless mud recovery have been developed to create a closed-loop system, allowing these sophisticated fluids to be used without discharging them onto the seafloor, ensuring the science doesn't come at an environmental cost. The ultimate goal and what we've found. So, why go to all this trouble? For decades, scientists have dreamed of a goal first attempted in the 1960s with Project Mohole, to drill completely through the Earth's crust and sample the mantle. The crust is just the planet's thin outer shell, the mantle makes up about 84% of Earth's volume. It's the engine of our planet, driving plate tectonics, powering volcanoes, and holding the original chemical blueprint of Earth's formation. Getting a pristine sample is one of the holy grails of geoscience. That complete journey hasn't been finished yet, but the discoveries made along the way have already revolutionized our understanding of the planet. Scientific ocean drilling provided some of the strongest proof for the theory of plate tectonics by analyzing core samples on either side of mid-ocean ridges. Expeditions aboard specialized vessels like the Japanese drillship Chikyu and the now retired JOIDES Resolution have drilled into critical subduction zones and active fault lines, like those near Japan, uncovering records of ancient earthquakes that help us understand the cycles of devastating tsunamis. Perhaps most profound are the biological discoveries. Scientists have found a vast deep biosphere teeming communities of microbial life buried deep within the oceanic crust, surviving without sunlight and extreme heat and pressure. These discoveries push the known limits of life on Earth and give us clues about how life might have originated here, or how it could exist on other worlds. And in 2023, an expedition accomplished a long-held goal by drilling into a section of the mid-Atlantic ridge where tectonic forces had pushed mantle rocks much closer to the surface, successfully recovering them for the first time. The quest to drill into our planet's mantle is far more than an engineering challenge, it's a fundamental pursuit of knowledge. Every foot drilled deeper is another page turned in Earth's hidden history. The chain of technology that makes it possible is just staggering. A GPS-guided ship that stays in one spot, robotic hands that work in crushing darkness, and a diamond-tipped drill that battles immense heat miles beneath the waves. This is the point where geology, engineering, and the timeless human drive for discovery all collide. While no one has yet managed to drill all the way through an intact section of crust to the mantle below, the ambition remains. The samples we hope to one day retrieve could unlock the deepest secrets of Earth's formation, the mechanics of earthquakes, and maybe even the very origins of life itself. We have spent centuries looking up at the stars, but it turns out some of the greatest unknowns might lie in the opposite direction, deep beneath our own feet.